which hosts this webinar. ISGAN is the short name for the International Smart Grid Action Network, a technology collaboration program of the International Energy Agency. ISGAN is also an initiative of the Clean Energy Ministerial, formally established in 2011. ISGAN creates a strategic platform to support high-level government attention and action for the accelerated development and deployment of smarter and cleaner electricity grids around the world. Currently, ISGAN consists of 28 contracted parties. They nominated representatives form the executive committee, headed by 2 presidium and assisted by 2 co-secretariat. The ISGAN work is formed by working groups that span from use cases to cost-benefit analysis, but also flexibility market, power system with transmission and distribution grids, and also the Smart Grid International Research Facility Network. ISGAN's vision is to accelerate progress on key aspects of smart grid policy, technology, and investment through the voluntary participation by governments in projects and programs. ISGAN activities focus on 5 principal areas: policy standards and regulation, finance and business models, technology system development, workforce skills and knowledge, users and consumers engagement. ISGAN facilitates the dynamic knowledge sharing, technical assistance, peer review, and where appropriate, project coordination among its contracted parties. The value proposition of ISGAN relies on conferences and workshops, policy and technology briefs, discussion and technical paper, casebooks, and webinars, like this one. Within ISGAN, virtual learning offers the ISGAN community means of rational and continuous skills update in the fields of smart grid. The virtual learning is proposed as a set of e-learning and reading code modules dealing with the entire value chain of smart grids. The webinar of today relates on how to integrate energy communities into the electricity system. And in particular, it delves into the findings of the OptiRec projects. The EU policy recognizes energy communities as pivotal for achieving energy transition goals. However, integrating this new actor into the existing electricity system landscape remains an open topic, especially as a large-scale energy community development reaches a critical mass impacting system and market operations. The OptiRec project investigates the technical and regulatory challenges posed by the large-scale development and integration of energy communities within the Spanish electricity system. The OptiRec project, Renewable Energy Communities as a Key to Accelerate the Energy Transmission, Optimal Integration from Citizen to the Grid. The goal is to ensure effective implementation of energy communities, and the aspects that are assessed are the design and internal operation of the energy communities participants and assets, the aggregation of energy communities, the integration into distribution networks, the participation into local flexibility markets, and the participation into the wholesale markets. The OptiRec project is a common project between 4 Spanish entities: Comillas Pontifical University, which deal with the local market design and energy community participation; IREC, that deals with the aggregation of energy communities and the integration into the distribution network; the Universitat Politècnica de Catalunya, that focus on the integration into the existing wholesale markets; and finally, the Universitat de Girona, that focus mainly on the intra-community forecasting and optimization. The main objectives of the project are the empowerment of energy communities as significant actors in the energy system by providing tools for an efficient management of flexibility at the community level, considering the grid interaction. The improvement on how energy communities and distributed energy resources can be integrated into the distribution networks in order to optimize their adoption, reduce the costs, and also strengthen the energy communities and ensure a suitable growth. Third objective is the promotion of user participation into electricity markets through energy communities by providing tools for designing effective local markets and identifying the conditions for the integration into the overarching power system markets. And finally, enabling the participation of energy communities in the multi-market structure of the wholesale electricity market through community virtual programming units. The speakers of the webinar today come from the IET, Institute for Research and Technology, Universidad Pontificia Comillas, and we have Syed Amir Mansouri that will present the models of multi-level integration, and Albert Farriol Salas from IREC, Fundació Institut de Recerca en Energía de Catalunya. We will have these two presentations, and as usual, you can use the question and answer tool to pose your questions, and the speakers will answer at the end of their presentation, and in order to clarify any doubt that you may have. And as usual, the recording of this webinar will be available through the ISGAN YouTube channel. Okay, now we can start with the presentations on the.
Okay. Hello, everyone. This is Amir Mansouri. I'm going to present distributed and hierarchical optimization frameworks for integrating energy communities into electricity markets. Exactly in line with energy community integration with existing electricity markets. So here I provide a slide to show you the differences between traditional and modern power systems. As you can see in the traditional power systems, we had a unidirectional power flow from transmission to distributions with passive demand side resources or consumers. And in modern power systems, we have a TSO and active DSO with active end users and many prosumers, distributed energy resources like PV panels, smaller scale wind turbines, or battery energy storage systems. And now we are going to activate these capacities and return it to transmission system. Here is an example for an active end user or a smart home or a smart building. As you can see, this building can manage its loads by actually it's thermostatically controllable loads or IoT-enabled appliances, electric vehicle batteries, and provide some services for the grid. So in some hours, it can receive power from the grid, and in some specific hours can provide services for the grid, services like frequency control, voltage control, congestion management services, and other flexibility services which are currently available in the demand side. So our motivations in this work are harnessing the maximum flexible capacities from cost-effective demand-side resources, such as smart homes, smart buildings, energy hubs, some smaller scale industrial parks, and etc. Another motivation is coordinating energy communities with system and market operators. The third motivation is enabling energy community members to provide grid services. The fourth is monetizing surplus power of community members, like smart homes. So we need to aggregate this flexibility and then transfer it for the grid. And the last motivation is motivating energy community members to invest in renewable energy and battery technologies, because only with this technology they can provide flexibility services for the grid. And also they need to controllable appliances. So the objectives are integrating local and wholesale congestion management and balancing markets. The second objective is designing mechanisms to simultaneously address energy imbalances and voltage regulation in real-time operations at both distribution and transmission levels. The third objective is developing original ADMM into adaptive multi-block versions with high convergence speed. The ADMM is alternating direction method of multiplier algorithm, which is very well known for its capability for implementing distributed optimization process, and this algorithm has a very high computational burden, and we need to make some changes in its nature to make it more compatible with our problems and to reduce its computational burden. And the fourth objective here is designing peer-to-peer enabled hierarchical models for integrating energy communities with local energy and congestion management markets. So in objective 3 and 4, we provided two different optimization model. The first one is an ADMM based or based on distributed optimization approach, and the second one is a hierarchical optimization approach. The hierarchical one has less computational burden, much more less computational burden than the ADMM one, but can't achieve global optimum solution, which we can neglect it in the real world. So here are the differences between hierarchical optimization and distributed based optimization approach, which we choose ADMM. So in overall hierarchical optimization involves a top-down approach where a central agent makes decisions that are then distributed to sub-levels for implementation, okay? But in contrast, distributed optimization involves multiple agents or nodes that independently solve parts of the optimization problem, often collaborating or communicating to reach a global solution without a central authority. So in distributed optimization problem, we are going to split the main optimization problem to several optimization problems with different agents. Each of them are responsible for a specific optimization, and they communicate their coupling variable to each other so they can achieve global optimum solution, but the computational burden is very heavy, and but in hierarchical one, the computational burden is very low, but we can't achieve the global optimum solution, which is more realistic, and we can neglect the global optimum solution in real world studies. The first model I'm going to present is a ADMM-enabled business model based on a distributed optimization problem. Here we provide an ADMM-based business model for integrating energy communities and electric vehicle parking lots with virtual power plants, distribution system operators, and transmission system operators. We have a 4-level problem here. At the first level, energy communities and electric vehicle parking lots schedule their day ahead. They are going to plan their day ahead and calculate their flexible capacities. Then they inform these capacities to virtual power plant, and in real time, virtual power plant can decide about the activation of these capacities. So energy communities and electric vehicle parking lots don't need to real-time coordination with DSO and TSO. and the VPP can do this for them, which is more realistic. And here we have implemented an ADMM between virtual power plants, distribution system operators, and transmission system operators for guaranteeing their coordination in real time. So we provided a 3-block ADMM, which is very challenging for convergence. We prepared an adaptive version, and we could guarantee the coordination in real time between these 3 authorities. And the coupling variables between these 3 agents are active and reactive powers, and dual coupling variable is lambda, which is the price of these services. And we also consider the coupling variable like active and reactive power services, as well as voltage, size, and angle as coupling variables between distribution system operator and transmission system operator. In this work, we performed a coordinated voltage regulation in line with the flexibility markets. So this is our case study, and we had a 57 bus IEEE networks connected to 4 PCC. And in each PCC, we had 4 distribution systems. Now we are going to the next slide. These are the specifications of our case studies. In cases 1 to 4, we had coordinated voltage regulation, and in the case 5, we had uncoordinated voltage regulation. And we investigated the different level of participation of demand-side resources in the balancing market. So this is the result from case 3, which all VPP resources are activated in the market, and we compared these results with case 1, and we found if all demand-side resources participate in the balancing market, we can significantly reduce the losses, power losses, in both distribution and transmission level. You can see these reductions. And here we compared the impact of participation of demand-side resources on the price of the flexibility services or balancing services. And you can see we could reduce them here. Active power locational marginal price and the reactive power locational marginal price. You can compare these prices in different cases, and you can see we have reduced these prices because these prices are dependent to their providers, and by unlocking this balancing services from demand-side resources, we could reduce these prices. And here we have the result of coordinated and uncoordinated voltage regulation. So if we consider voltage magnitude and angle as coupling variable between transmission system operator and distribution system operators, we can achieve more realistic results, as you can see here. Because where we didn't consider these coupling variables between TSO and DSOs, so you can see we achieved different results, which are not realistic. And most of works nowadays do uncoordinated voltage regulation, which is not realistic. And we showed this. And here we have active and reactive power exchange at PCC1 between 1 transmission and 4 distribution systems in downstream, and you can see the impact of coordinated voltage regulation on these services. And as we showed here, different amount for these services determined in case 4 and case 5, and you can see the impact of coordinated voltage. So we always have to consider voltage, angle, and magnitude as coupling variables so that we can achieve more realistic results. And here is the convergence process of our ADMM. And if you check here at write down, you can see our adaptive version for triple-lac ADMM achieves to global optimum solution in most of ours. But the original triple-lac ADMM has had many differences in all the hours of the scheduling from global optimum solution. So our algorithm not only achieves the global optimum solution, but reduce the computational burden and solution time significantly. And here I'm going to present another model, hierarchy, a P2P enabled hierarchical business model. And we had a 4-level problem here. At the first level, we had community members, which are smart homes. At the second level, we have an energy community operator, which is responsible for coordinating community members and also has a private space and private loads like a pool, gym, and this entity also has renewable energy resources and batteries and can participate in market and can exchange power bi-directionally by both smart homes and retailer. And retailer is in the 3rd level. And in the last level, we have DSO, which implement power flow and confirm the feasibility of all transactions in this market. And this market is designed for settling energy and congestion local energy and congestion management markets, okay, simultaneously. Take a look at this slide. You can see the interactions between different agents, and you can see we have energy community members here. These are energy community members. They can have bidirectionally power exchange with both energy community operator and retailer. And here we have energy community operator, which has its own assets and can have power exchange with both energy community members and retailer. And retailer has communication and power exchange with wholesale market here and the energy operator, community members. And after finalizing all these transactions, are gonna send the amount of power exchange at each node of the network to DSO. So DSO can implement a power flow and check the feasibility of these transactions. If DSO finds any infeasibility in this transaction due to the security constraint, voltage issues, or congestion, communicate the limitations to retailer. So retailer can communicate these limitations to all market parties. Then they can reschedule themselves and send new schedules based on new limitations to retailer. So this process is implemented to settle simultaneously both energy and congestion management markets. in the local level. So this is the execution process of this algorithm, which is hierarchical, and at the first iteration, the P2P power sharing among community members has to implement it, okay? And in the second step, and at the first step, each community member, which are smart homes, know their shortage and surpluses that not addressed in the P2P platform, so they can bring it to the energy community or the retailer. So they send their market strategies to energy community operator and retailers and ask them for power, sell or purchase, depend on their needs. And in the second step, energy community operator is going to schedule its own area, considering the programs received from community members and its own needs. And in the third level, retailer is going to be scheduled considering the programs received from energy community members and energy community operators, and can finalize its participation in wholesale market based on these programs. And in the fourth step, DSO receive the nodal exchange from retailer and perform a power flow. DSO can check the feasibility of all these transactions at the fifth level, and if DSO finds congestions, the operation is going to red mode, otherwise going to yellow mode. Okay. If as you may know, retailer can't calculate the power losses because this entity doesn't have access to the network information and doesn't have access to a power flow program, so can't calculate power losses. And when DSO gonna to implement the power flow, always find losses in this stage. Okay, so DSO gonna to inform the retailer about the power losses, so retailer can reschedule its transactions with wholesale market, purchase more power from wholesale to compensate for these losses. And here in yellow mode, DSO informs hourly losses to the retailer. Retailer, in the second step, retailer reschedules its power exchange with wholesale market. In the third step, retailer reports updated exchange to the DSO. In the fourth step, DSO performs power flow program again to check losses and congestion. If congestion found, go to red mode. Otherwise, finalize the optimization, because we don't have losses or congestion in this level. But if we found congestion, here we have to shift to the red mode. At the first step, DSO informs new restrictions to the power exchange to the retailer, and retailer inform these new restrictions to all market parties. In the third step, community members, which are smart homes, reschedule themselves considering these restrictions and pass their new schedules to the energy community operator and retailer. And the fourth step, energy community operators reschedule their exchange considering the members' updated schedules. At the fifth step, retailer reschedule its power exchange with wholesale market considering updated exchange received from community members and operators. At the fifth step, retailer reports updated exchange programs to the DSO. And finally, DSO performs power flow program, which always find losses here, because everything has changed and all transactions has changed, and DSO is going to calculate these losses and send the operation to the yellow mode. And after solving yellow mode, we don't have any congestion, we don't have any losses, and we can finalize the optimization. And we had 2 case studies for this model. The first one without finding any congestion, and the second one, DSO identifies network congestion. As you can see, here are the controlling parameters of our algorithm. When these numbers are 1, there are no limitations, and all network branches can use their 100% of their capacity. And but in the case 1, we found losses. You can see losses here. So DSO is gonna inform these losses to the retailer, and retailer here recalculated it's exchanged with wholesale market and compensate for losses. And you can see losses are 0 here. And we have these results for case 1. For example, for a smart home power exchange, we have exchange with the retailer with green, with ECO with blue, and in P2P platform with yellow, which transaction in P2P platform are only among members within the same community. And here we have energy community operator power exchange, which are with the smart homes in yellow and the retailer in blue. And here we have retailer power exchange with the energy community operators, the smart homes, wholesale market or pool market, which are the same, and renewable energy sources located in distribution level. And here we have a power balance for a smart home and energy communities. As you can see, a smart homes has PV, rooftop solar panels, electric water heater, and heating, ventilation, and air conditioning systems. These 2 systems are controllable load for a smart home, and they can schedule them, reduce their consumption, increase or etc. And they have fixed loads, which are lightning or something like that. They have battery and electric vehicles, and they have their exchanges with the energy community operator and retailer. So we are going to investigate second case study, which DSO identifies network congestion. So you can see we have both losses here at the first iteration of this algorithm, and also this limitation. You can see limitations here. For example, energy community number 2 can't have energy community at number 2 has to reduce its exchange to 45% at 11 p.m. with the retailer. This is the limitation. And here, energy community number 4 has to reduce its exchange with the retailer at 6 a.m. So these are limitations that found by DSO due to the congestion. And here are some limitations that energy community operators imply on their members, because their members need to change some exchange with the energy community operator. And we still have losses here, because these losses are going to be addressed in the last iteration of the algorithm. And here we addressed all the losses. Actually, retailer addressed all these losses. And we don't have losses, and we don't have congestion in the last iteration. And these are like the previous case, but power exchange of all market parties. And this is and these are power balances of energy community operator and smart homes or community members. And these are some conclusions. Unlocking the flexibility of a smart home of a smart end user significantly reduce expenses in the flexibility market, including congestion management markets, balancing market, or etc. The second remark is empowering a smart end users to provide grid services can generate substantial profits for them and motivating them to increase their solar panels and storage capacities. Achieving convergence in three-block ADMM is highly challenging and necessitates adaptive versions tailored to specific problems. The fourth remark is to achieve accurate and realistic outcomes, it is necessary to consider voltage and reactive power services in addition to active power services as coupling variables in ADMM algorithm. It is necessary to obtain realistic results. And lastly, I have to mention hierarchical optimization models are considerably easier to implement compared to distributed based models like ADMM, because the hierarchical based models has a very low computational burden. And for future research, I can suggest you developing digital platforms like Microsoft Azure or Google, all cloud computing based infrastructures, okay? All these digital platforms for designing decentralized business models for energy community members to facilitate their integration into real world electricity market, because only using these digital platforms they can provide grid services for the emerging local markets. And thank you for your attention. And this is the last slide.
And hi, my name is Albert. I'm from Iraq. I'm going to present the integration and aggregator of energy communities with the distribution network. But first, I would like to say thanks to Matteo for inviting us to this webinar. Thank you. This work will be split in 6 different subjects. First, the motivation, the methodology that we use it. We will describe the model used, the case study, the statistical results, and our conclusion. First, we go with the motivation. As we all know, the increased penetration of distributed energy resources at the residential level is transforming the energy landscape, empowering users and promoting greater energy autonomy. Also, new market exists, such as flexibility and peer-to-peer trading that are being developed to enhance the user participation and optimize the performance of the distributed energy resources. This is all really nice, but sorry, my mouse. This is nice, but there introduce a level of uncertainty that could impact the operational day-ahead decision of the distributed system operator or the DSO or the energy supplier, and this work will be focused on the mind of the DCO, because as a DCO, you before the energy communities, you knew really well what was the consumption pattern, but now if you merge like in an energy community and you do all these there, so the pattern will be changed, and as a DCO you would like to know how much this pattern will change and how there will be represented, and also at which hour could the energy community offer the flexibility service and in what quantity? Because not all the energy will be with you because the pattern changed. But okay, I accept that the pattern changed, but how much can the energy community offer to me as a DCO? And what quantity and what hour? And we want to do all of that without accessing to private energy community. So we want to do some predictions in the point of view of the DCO without the need of knowing everything about the energy community. So the user in the energy community can do whatever they want without us our knowing. So the methodology that we use it here. First, we created an optimization model to simulate the operation of an energy community. This is with the aiming of to replicate the future of the energy communities that we will have. So we used a time step of a wall model. This is the same as that we compiled a model to describe an energy community with a wall year. And this includes the consumption profiles, the electric load profiles, some thermal profiles, and some photovoltaic generation. Okay, we did all the model, we did all the computational things that we need to do in order to do the model. And then we will compare all of these results with the ones that include sensibility, the ones that include energy exchange, and then we aim to identify these optimization patterns in order to know what the energy community will do and to have all the information that the DCO we believe it is important and he wants. So now I'm going to describe a little bit the model description. As you can see, I'm not going to enter with all the constraints and all of the mathematical things, but I'm going to try to explain a little bit what we want. Basically, in an optimization model, you have an objective function. That is the most thing in the left. It's the thing that you want to maximize. Here, we want to maximize all the autonomy in the energy community. And all the other parts are what we call the constraints, the things that constrain our model or the things that are used to describe the real world assets or the markets. Here we have the loads, the market, and in the DCOs. When we go to the loads in red, you have two different kind of loads that we describe it in the model, the electricity loads and the thermal loads. I would like to thank you all the universities that joined the Opterec team because they sent us a lot of about this information, all these loads and the thermal loads. And also in the constraints that describe the market could be two different kind of markets. You could go to the flexibility market or you go to the P2P market, that is the trading market between the in the energy community. But these two markets have the same assets that are the photovoltaic, the electrical storage, the electrical vehicle, and the heat pump. The heat pump is also here in the flexibility and the P2P because there are some heat pumps that use gases, but there are some heat pumps that use electrical energy to function. So you could apply some flexibility here also. And from the part of the DCO, here is what we describe the network grid. I'm not going to explain a lot, but for the people that want to know how we did it, we used the second order comp problem. That's basically something that we believe it's a little bit known, or you can gather some information here. And now I'm going to explain a little bit the case study that we did. So we analyzed one energy community. In this energy community, we analyzed 56 users. We used a low voltage distribution network, and here, sorry, my cat. And here we have some photovoltaics of electrical vehicle head pumps, loads, but each user in the energy community have their own all demand, but we didn't wanted to show some results because we didn't want to take a lot of time here. So each one of the users have their own lives, how they work, and we just studied all as a group. And here is the combined energy demand in the energy community. This is the energy demand that the community sent to or is provided usually in the for the DCO. This is without all the application of the DIR assets. So this is what we probably will have right now, but it's going to change if you group in the energy community. So now I'm going to explain a little bit what are our statistical results that we take studying this model and all of this information. So basically, as the question that we would like to answer is how much would the energy community consumption pattern change by introducing distributed energy resources in the communities. So as said before, we have this pattern of demand that is something that it is well known, but now we form an energy community. We gather these distributed energy resources. How it's going to change? We did the model, we compiled the model, and this new energy community demand in the perspective of the DCO, what the DCO will receive as a demand is going to be this one. As we can see, it changes a little bit because now there is a valley in the electrical demand, but compared to before, but two distinct peaks of the demand has formed. So in the 10 to 15 hours, you have less energy demand, but in the other hour, there is a bit of increase. So the next question is, why this change? Because here in this graph, we can see the difference between the old one and the new one. So here you can see really well the valley that I was talking in the past slide, and a little bit of the two peaks, how this changes. So to answer this question, we see that this is basically, it's not 100%, but it's due to the electrification effect of both of the heating and the transportation sector. This is the electrical vehicle charging, and when you charge the electrical storage, when you use all the heat pumps, it is not one-on-one, but it is responsible for this valley when you need to change and when you change all the energy with the P2P market between the energy community, basically. So another question that it is important for the DCO PI is at which hour could the electric energy community offer flexibility service and in what quantity? Because we know that the load changed, but okay, could the energy community offer me some flexibility? I don't care that it changed, but could they service some flexibility? And the answer is yes. But the hours with the most flexibility are typically from 12 to 15 hours. During the other times, the energy community tends to not offer as much flexibility. So basically, in our study, we focused more on that 4 hours that are from 12 to 15. And here is an example of the hour 13. We did some box plots in order to know how much flexibility could the energy community do to the DCO. And we have seen that from the month 4 to the 8 are the ones that could offer more flexibility, or in mean, because I don't know how the bachelor degrees are in the people here, but this is a box plot. The line in yellow means that the mean, how in mean they are going to offer flexibility, in what quantity, and how much the black line is that how distributed it is. If you have a small box, you know more or less how much. So in the month 7, month 4 are probably the better months to know how much flexibility. But they offer flexibility, and you know at what hour and what months how much flexibility at the 13 hours, but not every day they are going to offer this flexibility and and this quantity, because you have some probability associated with this box plot. I'm sorry, I forgot one thing. The box plot are for the ones for all the days that they offer flexibility. If they don't offer a flexibility that day, or the flexibility is 0, they are not here in this graph. And now I come to the probability. This is how the probability of offering some flexibility at that hour 13. It changed between months because this is all the aggregated. At the first and the 12th month, as you can see, you have a less probability of offering flexibility. Although you have in the graph on the left, you have a relatively big box. It is not common to offer so much flexibility in that. So now it comes to the third question: could the DCO simulate the energy community behavior without access to private energy communities information? Because you want something like this. You would know how much energy is going to be sold from the grid as the DCO perspective. But in order to know this information, you need to know all the private information. You need to compute all the models. The models take a really long time. So there is something that you don't want to do, but you want to more or less have this approximation, because we approximate it as a normally distribution when you have a mu and a sigma. Mu is the mean, and the sigma is how much from the mu is split or separated from the. You want a lower sigma basically, so you know when the hours exact. But you want this, but you cannot have this. But you can also describe the power from the photovoltaic system, and as you can see, these are not the same. They are very different, but they act very similar. So with this information, that is information that is easier to achieve to everyone, because this information is basically a weather information. With a weather information, you could gather some of this information. Like, it's so similar that we created some statistical model to if you know one, you could know the other. So you could know the mu and the sigma. You could know at what time and how much is distributed, and these are the results. So using the day with the sales to the grid, we estimated for both mu and sigma. Mu is the mean, sigma is the distribution. One is I don't know how to say the word in English right now. Sorry. It's the other term from the normally distribution. The standardized error, sorry. So we have this formula, and the mu and sigma represent the time at which the energy will be sold to the grid. So basically, these are one of our strongest results. And now I will finish this presentation with the conclusion. With the penetration of renewable a shift occurs, as we can see. There is a valley due to photovoltaic generation and an increase outside that valley due to electrification. Sorry, my cat. This trend continues, demand patterns will keep evolving, and with a certain degree of probability, one could predict how much flexibility they could offer and at which hours. And from the DCO could establish flexibility without detailed user behavioral knowledge, granting freedom to both to the DCO and the suppliers for daily operational planning. And that's basically everything that we did from this study. And I will also thank all of you for your attention and for your questions if you have some, and to Matteo for inviting us. Thank you very much.
Thank you very much, Albert, for presenting the work, the activities that you addressed in the OPR project. There is a question from you. So I encourage the audience, the people that join the webinar, to put their questions in the question and answer tool. We have several of these questions that, well, one is specific for your activity, Albert. The others are for the ARM representation. That was the first one, but I think that I mean they can somehow also extend to your activity. But the first question for you is, if did you consider load shifting as a flexibility service, and if yes, why is that not possible during the two peak demand times?
15. Yeah. We used some load shifting as a flexibility service. We have it in the also as a constraints also with the head. So you can load you can shift a little bit of the demand, but the results are with all of these changes. So I believe, I'm not an expert, but I believe that the two peaks, it's because of all of this changing load and how this you impact with all of the batteries and the electrical vehicles. So this is not that you want to change these peaks, if it's not, for me, just the result of these implementing or creating all these batteries and all of the assets and how the price works, basically.
Okay.
I don't know if I...
Yeah. Yes. Thank you very much for the clarification. And well, there is a question for Amir, but Albert, if you see that this applies for you, also feel free to complement. Is how is flexibility quantified in your work, and if there is a particular metric that is associated to it?
Oh, yeah. Well, the flexibility is it's quantified with the energy that you offer, but we didn't want it to restrict the amount, so we created that. I didn't have, or we didn't want it to explain in deep detail. We created some methodology because we didn't want it to say we can offer a 20% of our thermal load, for example. So depending, we offer as flexibility as how much we are in the same temperature that we want. If we want to be at 24 and we are at 24, we will offer much more flexibility than if we want to be at 24 Celsius and we are at the 35, for example. I don't know. But it is, we didn't want it to say we quantified this with that and we put some ranges. So we wanted more flexibility model.
Okay. Thank you very much for clarifying this. And well, Amir, in your model, how did you consider the quantification of the flexibility? Is there a particular metric associated to it?
The market we designed was for addressing the energy imbalances in real time, okay? The differences for imbalances between generation and consumption in real time. So we just imply the white noise on the generation and consumption, and we made these imbalances, and then we asked participant to compensate these imbalances. So we just use the white noise using distribution probability functions.
Okay, thank you very much. And one last question for you is about the retailer role in your model. Could you please clarify which is the role of the retailer? Yeah, if it is like a third party from energy communities, and I think that this is the case, and which kind of services is considered to provide to the energy communities?
Retailer in our concept, retailer is an independent agent which is responsible for purchasing or selling power to the wholesale market. purchasing power from renewable energy resources within distribution system, and also has bidirectional power exchange with both community members and community operators. So intermediary agent, and can provide just power, based on the needs of distribution system operator and market participants.
Okay, thank you very much. And one last question from Albert, now. It's about the energy community's consumption pattern, how it changed with the introduction of distributed energy resource in the energy community.
Can you repeat the question, please?
Yeah, it's about the consumption pattern of the energy community. So how it changed with the introduction of the DERs.
Okay, thank you. Well, it's the graph that I show like 2 times. We began with this demand of load that we have, but when you apply some of the DER, it's when you create this valley and with the 2 peaks, because here you allow to do some of the P2P trading. So all the photovoltaic that you generate, it is not being bought from the grid. So, and the part that you have the supply or more supply than you need, it's when you trade. So it creates this valley at the towers that you have surplus of energy. And the other parts that you have the peak is when you use all the other assets that you were not using before, as the heat pump, when you are charging your electrical vehicle and your electrical storage. Basically, it's this changing.
Okay, thank you very much. And yeah, another question that applies to both of you is about the bidding prices, because from the audience, they understood that the power surplus from each user is known. And how do you model the user's bidding prices? Is this bidding price a parameter of the model?
I will start if it's okay.
Yeah, please.
So we used the price that you guys from the University of Comillas sent us. So for our is just a parameter that we know the prices from the market. So it is not it doesn't change when you are compiling the model. So it's a parameter that we know with some estimations.
Okay, thank you. And for the case of the AMILS model, how bidding prices are considered? Are they parameters or variables?
In my model, there are variables. Actually, we had 4 different models. In two of them are variables and 2 of them are parameters. Okay, and you want to consider them as variable. You need to use distributed optimization models or MPEC models, mathematical programming with equilibrium constraints. Otherwise, you have to choose hierarchical model and choose them, and you choose them and or you consider them as parameters. Yeah.
Okay. Okay. Thank you very much for this answer, and thank you very much for all the answers that you provided, and also for the presentation that you gave in this webinar. And so we are out of time, so maybe it's better to close the session. So thank you all for joining this webinar, and as usual, you will have the